All right, let's look at some reactions of alkenes. Before we look at that though, I just wanted to talk about how we draw mechanisms for organic reactions. And we use what's called curly arrows or curved arrows. What these arrows show is the movement of electrons, and the normal arrows we use are showing how pairs of electrons move. So we can show resonance structures using curly arrows. So resonance structures are two different Lewis forms of the same molecule, and resonance forms of a molecule contribute to the overall structure of that molecule. But we can also show reaction pathways. So for example, where a nucleophile reacts with an electrophile. Nucleophiles are nucleus loving, so they're seeking out sources of positive charge, whereas electrophiles are electron loving, so they're seeking out sources of negative charge, an electron poor. And so curly arrows allow us to draw movement electrons that signify where bonding changes are taking place. Now, you'll see these written in different ways depending on the textbook or the lecturer. But in general, the most precise way to draw curly arrows is we always start from a bond that signifies a pair of electrons, or we start from a lone pair of electrons. So over here you can see going from this resonance form of a nitro group to this resonance form, we've picked up a pair of electrons from this lone pair around oxygen, and we're moving them onto nitrogen. And then we're picking up a pair of electrons from this bond between nitrogen and oxygen and moving it out towards oxygen. You'll sometimes see a shortcut being taken where organic chemists quite often abbreviate this by showing the formal charge, the formal negative charge, acting like a pair of electrons. Now, it's not really technically as correct, but you'll often see this. And so where we show this negative charge and then a curly arrow moving away from that, that's really showing a lone pair of electrons associated with that atom that has that negative charge. So there's just a little subtlety there I wanted to point out. Okay, so in this case, we've got a pair of electrons on this oxygen going towards this carbon atom. So that signifies a new bond is being formed between that oxygen and the carbon atom. And then we've got a pair of electrons from this carbon-bromine bond being pushed out onto the bromine to show that that carbon-bromine bond is breaking, and we're getting new lone pair of electrons on that bromine and a formal negative charge. Okay, so let's look at reactions of alkenes. And by far the most important reaction of alkenes are electrophilic additions. So unsaturated molecules, alkenes and alkynes, can undergo what we call electrophilic addition. And the electrophilic part of this comes from the fact that the alkene or the alkyne is reacting with an electrophile. There's a few different types of electrophilic addition. There's halogenations, there's hydrohalogenations, and there's hydration reactions. They're the three most important of these reactions. So halogenation, we take a dihalogen, so it could be bromine or chlorine or iodine, and we react the alkene with that to make a dihaloalkane. Hydrohalogenation, we take a HX, so hydrogen bromide or hydrogen chloride, and we react that with the alkene to make a haloalkane. And hydration is where we take water plus a catalyst and we add that across the double bond to make a alcohol species. So these reactions, the electron-rich species, the nucleophile is the multiple bond that reacts with the electrophile. The electrophiles are electron-deficient species such as a proton or an acid that donates a proton. So these reactions of alkenes, let's illustrate them firstly with hydrogen bromide. So hydrogen bromide is a very strong acid and it's very polarized in organic solvents. So HBr, we can draw it with a delta plus on hydrogen and a delta negative on bromine to show that polarization across the molecule. So we draw a curly arrow that starts from the alkene as an electron-rich source and goes towards the hydrogen of hydrogen bromide, and then a curly arrow that starts from the bond between the hydrogen and the bromine and goes towards the bromine, breaking that bond. And if we do that, we're going to end up with a new bond between one of these carbon atoms here and the hydrogen, like so. So we've just chosen the right-hand carbon atom there. And what that does, it leaves behind a positive charge and an empty p orbital on the carbon that was part of that pi bond. And the other thing we've done is we've kicked out Br- as a leaving group. Okay, so this species with the positive charge and the vacant p orbital is what we call a carbocation. So that's a very electron deficient species, and it's highly reactive. So it's difficult to form, and once it forms, it reacts very quickly. So this first step, forming that very high energy species, is what we call the rate determining step. Because it's quite slow, so it determines the rate of the overall reaction. So when we form that species, it then reacts very quickly with the nucleophile. So let's have a look at this carbocation in a bit more detail. So a carbocation is where we have a positive charge on a carbon with an empty p orbital, and overall that carbon atom has only 6 valence electrons, so it doesn't satisfy the octet rule, and that's one of the reasons why it's so reactive. Now, some carbocations are more stable than others. They're all unstable to a certain extent, but tertiary carbocations are relatively stable compared to other carbocations. So what do we mean by tertiary? A tertiary carbocation, which is where we draw this 3 with a degree sign, so that is where we have 3 alkyl substituents on the carbon bearing the positive charge. Okay, so we have 3 alkyl substituents, carbon with R groups surrounding it and a positive charge, and that's a tertiary carbocation. If we only have 2 R groups, we have a situation like this, and that is a secondary carbocation. If we have 1 R group, that is a primary carbocation. And finally, there's only one type of carbocation where we have a carbon with 3 hydrogens and a positive charge, and that is a methyl carbocation. Now this is extremely unstable. The primary carbocation is a little bit better, but still so unstable that we hardly ever see them as intermediates. Secondary is a bit more stable, so they happen more regularly. They can be more easily produced. But tertiary carbocations by far the most important. They're the easiest to form because they're the most stable. So the overall trend is the more non-hydrogen or alkyl groups we have attached to the carbon that bears the positive charge, the more stable the carbocation. So that's down here. The more substituents, the more stable the cation. Okay, so we won't talk about that in more detail about why, but we'll just take that as a rule and we'll go forward on with this reaction. So the second step in this hydrohalogenation, or hydrobromination in this case, is that the leaving group from the first step, in this case Br-, acts as a nucleophile and attacks that carbocation. So it has a lone pair of electrons. We could draw those in if we wanted to. And it attacks that carbocation to form a new bond between carbon and bromine. So there's the new bond there. And that's our nice neutral stable species. So if we looked at an energy profile for this reaction, it would look like this. Firstly, we have an alkene and hydrogen bromide sitting at low energy. They go up through a transition state and then down in energy to an intermediate, which is high in energy because it's a carbocation. So in this case, that intermediate carbocation then can either go back to the starting materials, or lower energy pathway is that it reacts with the bromide ion to make the product. And so we've shown this in these pictures down here. So I've shown that down the bottom here, the starting materials, the products, and this high energy carbocation intermediate. So there it is there with its positive charge. Okay, so these reactions of alkenes are a situation where we can actually have some alkenes giving the possibility of more than one product. So for example, in this case, shown here, we've got an alkene that's unsymmetrical. So one end has 2 methyl groups and the other end has 2 hydrogens. So in the first step, where it reacts with hydrogen bromide, we can generate two different carbocations. The first, at the top here, is where the hydrogen has added to the right-hand side carbon. And so the positive charge is left behind on the left-hand side carbon. And that case is a tertiary carbocation. However, if we add the hydrogen to the left-hand side carbon, we end up with this product. There's that carbon-hydrogen bond. And the positive charge is on the right-hand carbon. So this is a primary carbocation. And they're not the same. They're not the same in terms of stability. We've already covered that. So the tertiary carbocation is much more stable. And so this top pathway is the favored pathway. And so this one is much more likely to occur because it's lower in energy. And so I'll say that one is stable and one is unstable, but of course all carbocations are relatively unstable, just a tertiary are much more stable than primary. And so we get much more of the product, so this is the major product of that reaction, because it comes from the stable tertiary carbocation, whereas this pathway gives only small amounts of the product. In fact, so small we don't see it at all in this particular case. And so these types of reactions were studied in great detail by a chemist named Markovnikov, and he developed a principle or a rule that tells us which of the products are more likely to occur. So his rule is just the reaction proceeds by the more stable carbocation, and this involves hydrogen adding to the less substituted carbon. So it adds the less substituted carbon so that the more stable carbocation is formed. So we've got that shown in more detail down here. Tertiary carbocation intermediate, primary carbocation intermediate. And sorry about this, but the I plus here is not iodine plus, it is an intermediate plus. So this is signifying one intermediate versus the other intermediate. So just in case there's any confusion about that. So Markovnikov's rule is really important in carbocation reactions because it allows us to predict which one of the possible intermediates is formed and therefore which one of the possible products are more likely to form. So electrophilic addition can happen with hydrofluoric acid, hydrochloric acid, hydrobromic acid, or hydroiodic acid, and we get the product formed in each case. And they all follow the same general scheme. So if we have a symmetrical molecule like this cyclopentene, there's only one possible carbocation that can form, because if we put the proton on the bottom carbon, we get the same carbocation as if we put it on the top carbon. And so therefore, the only possible product is chlorocyclopentane. If we do the same reaction with hydroiodic acid, we get iodocyclopentane, and so on. Okay, so if we do this with unsymmetrical alkenes, such as 1-methyl cyclohexaenone, then we're going to get two possible products. And Markovnikov's rule lets us predict which one will be the major product. So we should see in reactions of this type, the more substituted side will end up with the iodine added to it, and the less substituted side will end up with the hydrogen added to it. And so we get this 1-iodo, 1-methyl cyclohexane as the product. So there's a little typo there. Okay, and the minor product will be where the iodine is on the other carbon. So if we look at this in more detail, then we get the two possibilities: iodine on the more substituted side in the major product, and iodine on the less substituted side in the minor product. We do in this case get both the products, however the major product is the one that is predicted by Markovnikov's rule. Now these reactions where we have two different isomers being formed that differ in their connectivity, so they're constitutional isomers, this is an example of a regioselective reaction. So regioselectivity is where we have different outcomes from the one molecule undergoing a reaction. We can also do electrophilic additions using just halogens, dihalogens. So halogenation is most commonly done with bromine, also chlorine. And the bromine adds across the alkene with the bromine atoms being added to each of the carbon atoms that are involved in the alkene. And it's an example of what's called a stereoselective reaction, because we get a preference for one stereoisomer over another. So it can best be seen in the reactions of cyclic alkenes like this one here, cyclopentene. It reacts with bromine to give the 1,2-dibromocyclopentane as the trans product. So we get a stereoselective result. And the reason for that is that it has a particular mechanism by which the reaction occurs. The alkene attacks the bromine, and the bromine approaches the molecule from one face or the other. And so we get an intermediate formed, which is what's called a bromonium ion, a three-membered ring with a bromine now involved in two bonds to the two carbon atoms that formed this alkene. Because bromine normally only makes one bond, now it has a formal positive charge, and we've kicked out bromide minus, Br minus as the leaving group, and now the Br minus comes back in and attacks one end of that intermediate, and we break that Cbr bond to form the product. Because this bromine comes in opposite to the Cbr bond that breaks, we end up with the bromine in blue that comes in to make the second bond being on the opposite side of that ring to the bromine that formed part of this bromonium ion. So we get this trans arrangement. Another really important reaction of alkenes is reduction. So if we treat alkenes with hydrogen, we get no reaction, really, at any reasonable temperature. However, if we do this in the presence of a catalyst, the reaction is extremely fast, and the hydrogenation of an alkene happens even at room temperature. So we put a pressure of hydrogen in the presence of a palladium catalyst, and we add hydrogen across each one of those carbons involved in the double bond. So cyclohexene will become cyclohexane. And once again, we can get stereoselectivity in this reaction. So if we have a disubstituted double bond like this, then the hydrogen adds with each hydrogen atom coming from the same face of the double bond. So we get a cis product out of this reaction. So we get cis 1,2-dimethyl cyclohexane. And the reason why this occurs is it's thought that the metal surface, this palladium metal surface here, it binds to hydrogen and activates that hydrogen by sort of weakening that hydrogen-hydrogen single bond. So it's almost like hydrogen atoms on the surface of the metal. It also interacts with the pi bond of this alkene so that the alkene sort of sits on the surface of the metal like so. And then one of these hydrogen atoms sort of scoots across and forms a new carbon-hydrogen bond. And then the other end of that pi bond finds another hydrogen atom that adds to this carbon atom here, and both those are added to the one face of that alkene, and so we get this stereoselectivity. And we call that a syn addition. So syn addition is where we add two groups to a molecule where they both come from the same side. So reactions of alkynes are really similar to reactions of alkenes. They undergo pretty much the same reactions we talked about earlier. And once again, the stability of the carbocation formed is important in the reactions of alkynes as well. In reduction reactions, it's actually hard to stop the hydrogen being added at just one addition. So if we take an alkyne and we reduce it with hydrogen and a palladium catalyst, it will fully saturate the molecule to give an alkane. However, there's tricks that we can use to stop this reaction at just one addition of hydrogen across the alkyne. And so what we use is a catalyst called Lindlar catalyst. We won't go through the structure of this, but it's a palladium catalyst that's been poisoned so that it's less reactive, and so it's good at reducing alkynes, but it doesn't reduce the alkene intermediate that we would get in the normal reduction reaction. And so we can stop the reaction at the alkene stage. And so in the reaction of an alkyne with hydrogen and Lindlar's catalyst, we can get cis alkenes as the product out of this reaction. There's another way to reduce alkynes, which is using conditions developed by an Australian chemist named Arthur Birch. He was a Nobel Prize winner and also was given knighthood. So he was Sir Arthur Birch. He passed away a number of years ago now. But his conditions take a reactive metal such as lithium in a solvent of ammonia. So you have to do this at low temperature because ammonia is low boiling solvent. And it will reduce the alkyne so that we get a transalkene. So this is really important because it gives us different stereoactivity to the hydrogenation with the Lindlar catalyst. So there you go. Arthur Birch, one of Australia's most famous organic chemists. He developed this chemistry for reducing alkynes. It was also really important in reducing aromatic compounds, which is going to be the subject of another video. Okay, so hopefully that clarifies some of the reactions of alkenes and alkynes with electrophiles, particularly halogenations, hydrohalogenations, and their reactions with hydrogen over a palladium catalyst. Okay, so thanks for watching.